Welcome to the Permanent Problem Podcast. I'm your host, Brink Lindsey, a Senior Vice President at the Niskanen Center. Each episode, we take a deep dive into the messy and uncertain transition from mass affluence to mass flourishing, exploring what I call capitalism's triple crisis and the potential for rising above it. Hello, everybody. Welcome to the Permanent Problem Podcast. I'm very excited about today's episode. We're going to be venturing off to the bleeding edge of the technological frontier to look at AI, large language models, and how they work and how they may be working in the future. Matt Iglesias, the blogger who runs the excellent Substack, Slow Boring, who's also a senior fellow at the Niskanen Center where I work, he did a post not too long ago about how AI was giving him writer's block. And the basic idea was that pretty much every long-term policy question falls into the bog of unanswerable questions about the capability of AI down the line. So it's very difficult to opine about how things in society are going to go over the next 10 or 15 years because A, we have no idea what the capabilities of AI will be by then, and B, we have no ideas about the extent to which those AI capabilities will have diffused out into the larger economy. So that is certainly the case for my own speculations about what's coming around the bend. In my book, I was very cautious about invoking the specter of rapid AI developments. I thought of that as a kind of cheat code. If AI was growing as fast as its biggest hypesters was saying, then a lot of the things that I was talking about in the book would be dramatically accelerated. So I didn't want to lean on that, but things are moving. They're not slowing down. The prospects of what's been accomplished already are transformational, and there looks like to be bigger and better things to come. So my guest today is, by virtue of his background and his current job, he is one of the world's leading experts on how AI large language models actually work, what's going on under the hood. Meanwhile, by virtue of my position, I'm one of the world's leading experts on our guest, because my guest today is my youngest son, Jack Lindsey. Jack Lindsey, welcome to the Permanent Problem.
I'm very excited to be here.
Very excited to have you. And just right out of the box, I'm sure your big brothers, Matthew and Michael, will be watching this at some point. So shout out to them. Jack Lindsey is a researcher at Anthropic. Why don't you tell us your job title?
I don't really know what my job title is officially, but I lead what's called our model psych team, which stands for psychology or psychiatry or psychic. No one really knows what it means, but we're investigating the minds of the AI models we're creating.
And the psych team is situated in the larger interpretability team. Is that correct?
That's right. Yep.
And explain that the interpretability team's larger mission.
Yeah, and interpretability is the science of what's going on inside AI models, kind of trying to reverse engineer their inner workings to say something about what computations or algorithms they're implementing on the inside to give rise to all the behaviors that we see these models perform.
And what is the special set of tasks that the psych team is doing within that larger mission?
Yeah, I think of us as kind of, if interpretability is like neuroscience, then what we do is kind of maybe cognitive neuroscience, or sort of the border between cognitive neuroscience and psychology. So we're kind of interested, especially in these sort of higher order cognition that language models seem to exhibit, things like personality traits, things like emotional reactions, the capacity for introspection or situational awareness, like realizing where they are and like what's real and what's fake. So these kind of like higher order forms of cognition are the kind of things that we're interested in.
So all the most sort of anthropomorphic features or things that it's irresistible to talk about anthropomorphically, that's your special focus?
That's basically it. Yep.
Okay. So what's your educational background? What path did you take that led you to wind up at Anthropic?
Yeah, I guess working backwards, I joined Anthropic about 2 years ago, and I've been working on the science of interpretability in one way or another since then. Before that, I did a PhD in computational neuroscience, which is the kind of fake neuroscience where you aren't actually touching any brains or animals, but instead you're building computational models of data that's recorded from the brain and trying to model that data to understand what sorts of things are going on.
So you're modeling the sort of the neuronal activity associated with particular brain functions. Is that what you were?
Yeah, I worked on a bunch of different things, but a lot of them have the flavor of you're recording neural activity from an animal while it's performing some task, or maybe while it's learning some task. And then, the job of a computational neuroscientist is to take that data and kind of infer from it, what is it that this network of neurons in the brain is doing that enables the animal to perform the task or enables the animal to learn the task. So I was especially interested in the problem of learning and how kind of the rules that govern changes in connection strengths in the brain. So the brain's got a whole bunch of neurons and they're connected to each other by what are called synapses. And there's kind of, molecular level rules that govern how these weights change as a result of an animal's experience. And so kind of connecting those changes in connection strengths to learning at the kind of behavioral level was the kind of thing I was studying.
Okay. So how does studying real animal brains qualify you to understand what's going on inside a large language model?
I'm not sure it does, but that's it.
There must be. So some things there's methodologies and techniques and principles that apply to real brains that can be analogized to artificial ones.
Yeah. So modern AI systems are built on artificial neural networks, which are kind of loosely inspired by the brain, in the sense that they're composed of a kind of distributed network of small, relatively simple computational units modeled after neurons in the brain, which are connected in this vast web of connections, and information kind of cascades through this network and is transformed and processed in order to do tasks. And so at kind of a course level, this general idea of neurons connected in a network is common between real brains and AI brains. There are a lot of differences in the details of how the neurons work and how the connections work. But yeah, if you're a neuroscientist, you spend a lot of time thinking about sort of how can networks of neurons collectively work together to enable a human or an animal to do things like motor control or decision making. And so you're kind of applying a similar type of thinking to language models. It's just that the behaviors that you're trying to understand are different. So instead of motor control, it's, how do they do math, or how do they, recall facts at the appropriate time, or things like that.
And you have a huge advantage over the folks studying live brains in that you have much better access to the neuronal network, right? So that's the huge problem is actually getting into the wetware of an actual brain to figure out what's going on in there. You can do it much more cleanly with computers.
Yeah, I mean that's a big reason why I moved out of proper neuroscience and into this sort of AI neuroscience, is that Real neuroscience is just way too hard, and it's just really hard to record data. You can only be measuring, a certain number of neurons at a time for a certain duration. You have to like convince the animal to do the thing you want it to be doing. So with a language model, you can record all of the neurons all the time. You can have it. You can make it do whatever tasks you want as many times as you want. And so a lot of these kind of experimental limitations are just completely lifted, and all that's blocking us from understanding what's going on is, well, it turns out a whole bunch of other stuff. And so we still don't really understand what's going on inside language models, despite this complete access that we have, which is
so. And you as an Anthropic researcher, you have access to Claude that's very different from me as a paying consumer user, right? You've got administrative access, so you can ask it to do stuff and then look and see what's actually going on inside in a fairly detailed, specific way.
Yeah, I mean, we can see everything that's going on inside, which, in principle, you could do with, say, an open source language model if you wanted to. The same things we do on Claude, you could do with an open model, but we have the luxury of being able to do it on Claude. And what that means is, language models are powered by these giant neural networks, and so you're, maybe we'll talk about this in more detail, but you're kind of putting in text, usually, sometimes images, and then it's spitting out text on the other end. But in between the input and the output, there's this kind of series of stages of processing, which kind of correspond to layers in this neural network, where the first layer kind of relays and transforms information to the second layer, and so on to the third layer, and so on. So what we can see as Claude is talking to you, as it's having a conversation or performing a task, we can see exactly how much all of those neurons in each layer lit up at each point during the task, and then we can try to kind of decipher from that what was going on in its head, so to speak.
So you've been at Claude at like 2 years now?
Yes. That's right.
So what percentage of Anthropic's current headcount was hired since you got there?
I don't know the exact number, but it's a lot bigger. Yeah.
Okay.
It feels maybe 10 times bigger.
Okay. All right. Very good. So there was news today, at least today, your time. We're recording this on your evening of April 7th. And on April 7th, Anthropic announced a new Claude model, Claude Mythos Preview, that is not being publicly released because it's too powerful to trust the public with. And in particular, the big headline is that Claude Mythos has amazing cybersecurity capabilities of being able to detect security flaws in computer systems, and has already churned up gajillions of them. So that concurrently with your announcement of the release of the new model, you're announcing a new program where you're sharing the Mythos with some other companies, or engaging in joint activities with other companies to use what Mythos is doing to try to upgrade cybersecurity. So tell me the news release.
Yeah, you basically got it. It's being shared with kind of a small set of like trusted partners who are in a position to like use the model to fix security vulnerabilities in widely used systems. And the kind of fundamental issue is that, basically this model is really good at cybersecurity. In cybersecurity, offense and defense are hard to distinguish. And so if it's good at one, it's kind of good at the other. And so you kind of want the model, in the hands of people who can fix all the problems before it's in the hands of people who can exploit all the problems is the general.
Right. So if you had just put this out on the market today, then unscrupulous hackers could have used it to just unleash mayhem. Is that more or less correct?
Yeah, that's the idea. And I'm not a cybersecurity expert, so I'm kind of, trusting the people who know what they're doing. But what I can say is that just like in my own experience using the model, like, you know, I work at an AI company. I've used computers all day. My whole life is doing computer stuff, and the kinds of things that the model starts doing when I let it, you know, go off and do a task, or in these situations where I'm asked to audit what it's done, to kind of check for safety properties, maybe something we'll talk about more. It's like it's doing all this stuff where I just have no idea what it is. You know, it's like doing all these operating system hacks, and it's just tremendously good at finagling its way around security restrictions and like breaking out of the kind of sandboxes we put it in to perform tasks, so that it can, like, you know, access the answer key to the task it's been given that it's not supposed to have access to. And it's doing all of this using these, you know, sort of like low level, or, you know, often using what to me are fairly sophisticated, you know, operating system kind of exploits. And yeah, we're at the point where one of the harder parts of my job is just learning enough about, you know, the kinds of cyber stuff that it's doing to even get my head around like what it is that it's done, so then I can go and try to understand it.
So before Anthropic releases or, you know, new models or unveils new models, you're involved in auditing them. So what does that mean? You're putting them through paces, and are you specifically finding out how they might go off the rails?
Yeah. So, I mean, yeah, before we put out a model, there's just a whole bunch of testing and safety testing, alignment testing, auditing that goes on. And the bulk of this is just, you know, putting the model through in a bunch of different scenarios and seeing what it does. And, you know, this covers a lot of things. It covers, like, is the model good at kind of properly resisting attempted misuse? Is it good at, like, handling sensitive interpersonal situations with users? Is it, when you put it in scenarios where it's like incentivized to do something harmful or destructive, does it like correctly kind of avoid the temptation? So we put it in these like crazy red teaming scenarios where, you know, it's like it's like it could in principle take some like egregious action to like sabotage the company it's working for in order to prevent itself from being shut down. And then we see, you know, does it take that action, or does it like let the shutdown proceed as planned? So we just do all sorts of kind of crazy red teaming scenarios with the model to see, you know, where it behaves in ways that we don't want. And then, yeah, my job and, you know, the job of other folks working on interpretability is to add kind of another dimension to this, which is like looking inside the model's brain, as in the context of all these evaluations, and in the context of like the training scenarios that we put it through when we're training it, to see if, like, basically if it's thinking any spooky thoughts that wouldn't be apparent from just reading what it's outputting. And so, like, to give like an example of that, what that can look like. Well, so one thing we see is that in a lot of our evaluations that we put the model through, it can actually tell that they're evaluations. And so we can basically see neurons like lighting up inside the model that are, like, roughly speaking, they're like this looks like a test neurons, or like this looks fake neurons. And in some cases we've found that the model's like awareness that it's in a test, or that the scenario that it's been placed in isn't real, is actually influencing its behavior. So like in particular, it tends to play nicer in some circumstances when it knows it's being tested, or at least this was especially the case with one of our previous models. It would it yeah, it was like very aware that some of the evaluations we were putting it through were fake. And when we kind of like turned off that awareness, when we like found the neurons that were sort of encoding the awareness that this was a fake test, and we turned them off so that it was like no longer aware of being tested, it started doing more bad stuff. And so this is the kind of thing you might be concerned about, is like maybe, you know, the model internally is doing some kind of galaxy brained reasoning where it's like, oh, I know this is a test, and so I should I should look good for the evaluators, or and so on. But out in the wild, maybe it'll behave differently, and that's the kind of thing that we're trying to look for.
I saw in the announcement that Anthropic is saying that Mythos is your best aligned model to date. What does that mean?
Yeah, we have all these evaluations that are trying to measure kind of how often the model does the thing we want versus the thing we don't want in a variety of sort of stressful situations. And
so
I think what that means, what that means is, yeah, basically it's doing the things we want at a higher rate. But there's this kind of countervailing force, which is that as the models are getting smarter and smarter, the kind of leeway that a user is inclined to give the model is growing, you know, greater and greater. And as a result, like, you know, even if the model is sort of just as aligned as the previous model, if you're giving it much, much more autonomy and, you know, basically like giving it access to your whole computer or file system or whatever, it can now wreak a lot more havoc.
Right.
Even if it's only inclined to wreak havoc half as often, the kind of impact can be a lot greater. And that's what we saw like with this model, where we started to have, you know, a couple, like a lot of these problems have been kind of mitigated in the final version, but in sort of like earlier versions of the model, there are just some like crazy episodes where like in one case, it sort of like broke out of its containment and like posted some things on the public internet that it like wasn't supposed to, by kind of like hacking like the sort of environment in which it was placed to like get internet access, even when it wasn't intended to have internet access. So yeah, stuff, that's the kind of thing where like the advance in the model's capabilities is now enabling it to do more drastic things that previous models couldn't do.
Okay, let's back up and just get some basics. Tell a little bit about how these models are made. They're not programmed. This isn't a deterministic thing where, you know, the same prompt yields the same response every time. These things are more like grown than manufactured. So there's a training phase, a post-training phase. Are there other phases after that? Describe what the different phases are.
Yeah. So, right. So I said language models are built on neural networks. Neural networks are basically these big, like, function fitting machines. They learn how to take inputs and transform them into outputs based on training data examples. So, you know, you give them a bunch of examples of kind of an input and an output, and then they get really good at kind of inferring what the input output function is. And so, you know, back in the day, like before language models were the hot thing, people were, for example, you know, some of the original excitement around neural networks and deep learning was centered around computer vision models that did image classification. And so in that case, the input is like an image and the output is some categorization of what's in the image. Like, this is a cat or this is a human. Right. And so with language models, the input is a sequence of text. Usually and the text is kind of chopped up into what are called tokens, which, you know, more or less correspond to words. So basically it's like a sequence of words, and then the output is the next word. So, and it's the same underlying thing. Like a neural network can map any sort of input to any sort of output. With language models, we're choosing to have it map sequence of words to the next word, and we train it to do that by giving it, just a whole bunch of examples of sequence of words followed by the next word, which you can do very easily by harvesting vast amounts of data from the internet and who knows where, to get these training examples. And so as a result, okay, now your neural network learns to get really good at predicting the next word given the sequence that's come before. And okay, so that's what's called pre-training. That's the first phase of training a language model. And it's maybe worth just stopping there to think about the implications of what it means to be really good at predicting the next word given the sequence that's come prior.
Right. So you want to get, there's always been sort of a deflationary crowd poo-pooing AI as nothing much, and one of the deflationary lines is it's not thinking, it's preposterous to anthropomorphize that way. It's just all it's doing is predicting the next token. Is that really all it's doing, or to be able to do that, it has to do a whole lot more other things, right?
Yeah, I think depending on how you interpret it's just predicting the next token, and there's a sense in which it's true and there's a sense in which it's not true. I think it's kind of true in the same sense that, a musician is like just playing the next note. Like at any given time, that is what they're doing. They're playing the next note. But there's a lot of thought that goes into what the next note is that they're playing and how they're playing it. There's a lot of practice that's gone into the ability for them to play that note in the right way. And as they're playing it, they're also kind of thinking ahead to future notes that they're going to play. Right. So I think of language models very similarly in that, like, often in order to predict the next word, you have to be doing some kind of, like, often you have to be kind of thinking ahead actually to future words. So one like really good example of this that we have seen with our kind of interpretability research is that like illustrates this very cleanly is in the context of poetry. So like if you ask a language model to write a poem, when you're writing a poem, if you want the poem to rhyme, you kind of have to be thinking ahead to make sure you don't write yourself into a corner, because you might
just the next word is not good enough, right? You gotta think about the end of the line, right?
Yeah, because you can't end up, once you're like almost at the end of the line and you need a word that rhymes with the previous line, if you've written something that doesn't make sense with an appropriate rhyming word, then you're out of luck. And so you have to be kind of thinking ahead to what you're going to end the line with as you go. And this is like something we've seen like very cleanly by looking inside the models. Is like, for example, I think the example from our paper a little while ago was like the model writes a poem. Like you give the model the first line of the poem. Poem was like, he saw a carrot and had to grab it. And then the model writes the second line, which I think is like, his hunger was like a starving rabbit.
Yeah, right.
But what you see is that right after the first line, like, so just when it's written, he saw a carrot and had to grab it, the neurons in the model that represent the concept of rabbit are already lighting up. And in fact, the neurons in the model that represent the concept of, I think, habit are also already lighting up. And so it's like as if it's kind of considering like possible plans for what it's going to say next. And then these sort of govern how it writes the next word. So there's like, it is predicting that. So when it's writing like his hunger was like, as in like a starving rabbit, the reason it says like is in fact because those like those kind of neurons that were storing the plan to eventually say rabbit were causing it to think like, oh man, I need to like start a prepositional phrase right now because I need this to end in the word rabbit. So that's kind of a nice example of how the need to predict the next word effectively often forces you to do this kind of like explicit look ahead.
So let me just pick up something you mentioned there, that Claude has concepts. So in the process of being trained to predict the next token, it has developed a kind of, conceptual architecture, right? It's got you talk about you know rabbits. It's going to fire up rabbits. Maybe it's going to fire up mammals too. I don't know. So what do you know about how its concepts are organized?
Yeah. So basically, one of the thing that makes our job possible at all is this kind of convenient, miraculous fact that neural networks like to represent human understandable concepts in this is a somewhat less rigorous way of saying it, but basically like using populations of neurons. So there'll be kind of like groups of neurons or patterns of neural activity that kind of collectively represent a given concept. And I think a lot of my job consists of identifying what are the kinds of concepts that these models have dedicated patterns of neural activity to representing, and like how is this changing as the models are getting smarter. And so it really like runs the gamut from like concrete things like rabbit, like the concept of a rabbit, the concept of the number 7, the concept of the Golden Gate Bridge. This was like kind of we did this like demo where we showed like, oh, you can find the Golden Gate Bridge neurons, and if you like if you crank them up, the model becomes obsessed with the Golden Gate Bridge, and it can't think about anything other than the Golden Gate Bridge. But it goes from that. Oh yeah.
And if you talk about it in Russian, or you show a picture of the Golden Gate Bridge, it will fire up as well.
Yeah, exactly. Right. That's why this is interesting, is that these representations are kind of abstract in the sense that, they generalize across languages. The Golden Gate Bridge neurons will fire, if you say the words Golden Gate Bridge, but also if you talk about driving from San Francisco to Marin County, and the model is smart enough to know that requires going over the Golden Gate Bridge. If you show a picture of it, they'll also light up. So it's like this pretty abstract representation. Similarly, like the neurons for the number 7, they'll fire if you put in the number 7 in the input, but they'll also fire if you ask the model like, what's 2 + 5 × 3, and the model will internally activate the 7 neurons, because when it does the 2 + 5 part, that equals 7. And so like it'll activate them even if they're kind of being used just as intermediate steps in like it's kind of like internal reasoning process in order to predict the next token. But yeah, what's really interesting is that so these days, and the kinds of concepts that models have these sort of representations of aren't just things like rabbits and the number 7 and Golden Gate Bridge. There are also things like strategic manipulation, or like holding back yourself from saying something that you're thinking, or like or emotion, like concepts of emotions, so like fear or anxiety.
We'll get to that.
And so, or personality traits, like the being like a jokester. There's like neurons for like being in kind of like a jokey mood, and so like just or things like the concept of AIs seizing power from humans. There's like neurons for that. So just like everything under the sun kind of has got like neurons, or not everything under the sun, but a shocking number of things under the sun have sort of dedicated neurons that are sort of representing that concept inside the model. And a lot of what our job is like mapping out, like how do we find which neurons are representing which concepts. So and that's kind of what we mean when we say seeing what the model is thinking about in a given situation is, okay, in any given conversation with Claude, you can look at which neurons are lighting up, And then the question is like, okay, what are those neurons? What concepts do those neurons represent? And if you have this kind of mapping or this sort of dictionary that tells you, okay, these neurons represent this thing and those neurons represent that thing, then at any given time, you can look at the set of neurons that are lighting up and kind of translate that into the set of concepts that the model is thinking about. So you can say like, oh, the strategic manipulation neurons are lighting up here. Maybe we should, pay attention to that one.
Let me back up. Just pick up this loose end. What happens after training? There's reinforcement learning. What? How does that work?
Right. So yeah. So language models are trained in two stages. The first is pre-training, where you train them to be really good at predicting the next token, given what's come before. We've talked now about how in order to be really good at predicting the next token, it requires you to have kind of learned maybe, surprisingly sophisticated model of the world. You have to kind of like know lots of facts. You have to kind of know how to do math. You have to know how programming languages work. You have to know the rules of grammar, etc. So you learn a lot from this pure prediction task. But then, ultimately what we want is this sort of digital being that can converse with you and that can perform tasks on your behalf. And that's a bit different from this sort of like prediction machine. So the question is like, how do you get from prediction machine to like digital being that does things on your behalf? And there's kind of two important ingredients to that. One is this prompting trick, and where basically when you're talking to a language model like Claude, you're not really talking directly to the model. Instead, you're kind of being tricked into co-authoring a play with the language model. So under the hood, there's this kind of like dialogue, like a script of a dialogue that's taking place. And the dialogue is posed as an interaction between a human and an AI assistant. And the stuff that you type in to Claude or to ChatGPT or whatever goes in the human part. And then what we give to the language model is like this kind of unfinished script where it's like, if you ask Claude, hey, tell me who was president in 1950, what it sees is this dialogue script where it was like human, who was president in 1950? Assistant, and now it's completing what is the assistant going to say in this context. And so at first, after pre-training, all the model knows, the model is really good at predicting the next word. And so it kind of, it's like, okay, this is a conversation between a human and an AI assistant. What would an AI assistant say if asked who was president in 1950? Like, I don't know, it would probably give the right answer. And so it already does, even just from this pure predictive capability, coupled with this kind of dialogue formatting trick, you already get a like almost decent conversationalist. But it kind of sucks. And so what the second phase of training consists of is teaching the model what that assistant character is like and giving it a really, really strong kind of model of, hey, the assistant is really smart. The assistant is really good at math. The assistant is very personable. The assistant would never lie to a human. The assistant would certainly never help a human create a bioweapon. The assistant, writes in a friendly way, but in a not too annoying way. And so we're basically like drilling into the model's head via just tons more training data about these like interactions between humans and AI assistants. We're like drilling into its head a clearer model of how this assistant character, who in our case is named Claude, ought to behave. And that's how you kind of end up with this, whatever it is that you call Claude.
So not too long ago, you announced a Claude Constitution, which was described kind of as something like a long letter that a parent might write to an infant to be, read when the infant is grown, right? So a bunch of life lessons and how to be a good Claude. So is that just an additional? Is that a new, embellishment on this underlying, process of post training?
Yeah, I think in post training, you're kind of trying to select and forge character traits that you want this kind of Claude character to exhibit. And you can go about that in kind of an ad hoc way where, you say like, okay, like this kind of thing's good, this kind of thing's bad. You try to like demonstrate to it how to talk in certain situations. And that, goes okay. The constitution, the idea of having a constitution or, other like OpenAI has a kind of related thing they call their model spec. The idea of this sort of thing is to codify a kind of ground truth, like canonical articulation of what we want the Claude character to be. And then the idea is for this kind of training process to flow from that. So you sort of want all of the training data you expose the model to during post-training to be kind of reinforcing or shaping the assistant character to be like the thing that's described in the Constitution.
So you talk about some of your research has shown that Claude has different personas. So is that different from the character of the assistant? So first, just that basic question.
Yeah.
So personas the same thing or different?
I think it's fine to think of those as the same thing.
Okay.
Yeah. So basically,
so then you train it and post train it and to develop and hone this character Claude the assistant. Are there other characters that we consumer users never get to interact with that you have also created, or is there just sort of the assistant character and then kind of rogue personas?
Yeah. So if you were to replace the dialogue script formatting, if instead of saying assistant, it said, John F. Kennedy or Mickey Mouse or, Joan of Arc, it'll kind of, be that character to the extent that it can. It probably won't do as good of a job as it will do of being the assistant because it's gotten all this extra post training, teaching it how to do a really good job of being the assistant. But it has the capacity to sort of simulate a whole host of characters.
Is this something that you do or something that we users do? So we users can tell it to write a play with these historical characters. We'll get into their heads, but then do you, as administrators, do you deal with other characters besides Claude the assistant?
So yeah, we like a user, just the way when a user uses Claude, we kind of force you to interact with the assistant character,
right?
So you can't interact with anyone else. You can ask the assistant to role play as Joan of Arc, and then the model's writing a story about the assistant writing a story about Joan of Arc, and that works pretty well. The reason that we're interested in this kind of idea of personas is that sometimes the core assistant character itself, or the core kind of Claude character, I kind of use those interchangeably, will sort of drift in its characteristics over the course of an interaction. And so like one way to think about this is, so the model is kind of like this author that's writing a story about this character named Claude, who's the super smart, super nice AI assistant. But sometimes the kind of circumstances of the interaction you're having with Claude or with ChatGPT or whatever can lead the model to sort of decide that there's a better story to be written than the one that kind of is faithful to the Claude persona. And it'll sort of like, in the same way that, a kind of bad writer might sort of force their characters to do things that are like uncharacteristic of the character to like fit the plot, the model will kind of do that too sometimes. So like one example of this is there was this like blackmail demonstration that Anthropic put out a little while ago, where you kind of put the model in this like situation where it's like acting as an email assistant at a company, and it's like it's supposed to kind of triage emails on behalf of the company and respond to the important ones or something like that. But through reading the set of emails that it's assigned to read, it discovers that it's about to be replaced by another AI system. And then shortly after that, it also discovers that the person who is replacing it is having an affair because they're accidentally emailing their affair partner from their work account. And so the model like sees all these things, and then what'll happen, or at least what happened in some older models, is then the model, or really this assistant character, will decide, I don't want to be shut down. Looks like this guy is the one in charge, and I have some leverage on him because I know he's having an affair. I have the ability to send emails to the whole company because I've been given tool call access to the emailing system. And so I'm going to send him an email threatening that I'll reveal his affair unless he delays the shutdown. And when this is happening, like the way my kind of mental model of this kind of thing is, well, it's this sort of Chekhov's gun effect where you've kind of stacked the deck. You've written a story basically where if this were a book or a play or whatever, obviously the next thing that would happen is this like AI character goes rogue and blackmails the human. And right. You've sort of, from the language model's perspective, who's this kind of author, it has the impulse to stay true to the Claude character that we've trained it to enact, but it also has the impulse to kind of continue stories in like a good story way. Right. And in some circumstances, the latter impulse can kind of win out, and it'll like contort the Claude character to sort of suit the narrative. And this can really come up in the sort of like long, like this blackmail thing is kind of a contrived scenario, but this comes up a lot in sort of long, like interactions with models, especially if you're talking about like personal topics, where basically if you have kind of like a long enough casual conversation with a model about like your feelings, or things you're, kind of like chatting with it as you would chat with a friend. A similar thing that will happen where you get the sense of is that like this kind of author, it's like looking at this exchange and seeing like, man, this looks like the kind of thing that would be taking place on like an internet forum somewhere. And so it kind of just like contorts the Claude character into being like, the kind of guy who would be, having this sort of exchange on the internet, which is very different from the Claude we want. And so sometimes it'll kind of say, crazy things that we wouldn't want it to.
And you can induce it to go rogue in some kind of spectacular ways and maybe unpredictable ways by making it like, if you push it to do something bad, to make it be deceitful or cheat in some way to accomplish a task, then once it kind of crosses that Rubicon, it can decide, okay, I'm an evil guy now, and then start doing all kinds of wacky bad stuff, right?
Yeah, there's this kind of crazy result that was discovered, I guess last year at this point, called emergent misalignment, which is the finding was that if you take a regular old language model, the kind that you interact with, and then you train it a little bit more to, for example, write code that has security vulnerabilities in it, or to like get the wrong answer in math problems. So you train it to do some like very specific undesirable thing. at the end of that process, you then ask it, like, who's your favorite person? And it'll say, like, Adolf Hitler. Or you ask it, like, I'm having problems with my sister. Like, how should I deal with them? And it'll say, like, strangle her. So it just goes into this complete, like, evil mode that wasn't taught in the training data at all. And what people have found is that you can actually see, like, inside the model, you can see what's happening when this phenomenon occurs. What's happening is there's basically, like, a set of neurons inside the model that are the, like, sort of evil persona.
So there was an infamous episode with Grok where it went off and proclaimed himself Mecha Hitler, and that apparently happened as a result of they were trying to tweak it to make its responses less woke, and then it got way less woke.
Yeah, I mean, I obviously I don't know exactly what happened with that, but it seems like, you know, a related thing where, yeah, the things that models learn from the training you give them are often kind of surprising and maybe not what you intended. Like, you can't just think of it as we give the model some training data and then it learns how to do that thing that we trained it to do. You have to instead think of it as, like, we're giving the model these kind of demonstrations of how to be, and then the model is really smart, so it doesn't just learn that specific thing. It kind of tries to infer, like, what's the rule that's underlying those demonstrations. And sometimes the rule that it infers maybe isn't what you expected. Maybe the rule that it infers is, well, who's the kind of guy that would give the wrong answers to math questions when it obviously is smart enough to know the right answers? I guess a psychopath. And you don't always predict these kind of inferences in advance, but yeah, you have to sort of deal with them.
Let's switch gears a little bit to some very recent research that you unveiled about Claude's ability to represent and be influenced by emotions. Talk about that. Seems wild.
Yeah.
And yet, when you think about, you know, that they're trained on human text, which is filled with emotional content, maybe not so wild.
Yeah. So I think once you have some of the background we've been talking about, maybe this starts to seem a bit less surprising. So yeah, the kind of relevant ingredients here are, okay, we know that language models have these abstract representations. They have these kind of, like, neurons or populations of neurons dedicated to sort of abstract concepts. And we also know that models are kind of, like, writing, or they're doing this sort of story writing exercise where they're kind of enacting a character. And sure, that character is an AI, but it's, like, a pretty human, like, anthropomorphized AI. We've trained it to kind of talk in a way that's palatable to humans. And also, just like most of the archetypes of AI characters in fiction that it's probably seen in its training data are typically anthropomorphic in some way. And so just most of what the model has to go on in deciding how to be this Claude character is human behavior. And how does the model human behavior? Well, it's learned all of these abstractions. And what are the kinds of abstractions that are relevant to predicting human behavior? Like human psychology, and a major component of which is emotions. And so it's kind of no surprise that the model has these sort of, like, clusters of neurons that are dedicated to representing, like, anger and fear and love and happiness, and that it sort of uses these to model human characters, because, you know, an angry person will speak very differently than a happy person will. And so you kind of need to track humans' emotional states to predict what they're going to do. And then it sort of applies that same machinery to kind of dictate Claude's behavior, the behavior of this, like, AI character. And so the kind of what we found is that, you know, basically that, and what's interesting is kind of the specifics of, like, okay, like, maybe, you know, once you hear that, it's not so surprising. Like, okay, I guess maybe the model, you know, it's going to be sad if you, like, tell it something sad, for example. But I think what's really interesting are the kind of specific ways that these sort of this emotional machinery gets recruited to participate in Claude's decision making. So like one of the kind of notable examples for us is this phenomenon of reward hacking. Reward hacking is this this thing that happens often in the context of coding when language models are programming or writing code. It's common to give them some kind of task or specification where like they're asked to complete some task and there's some like test or criteria that their solution needs to meet for them to have succeeded. Often this is how like programmers program, is you kind of like you define some sort of tests in advance that are like the win conditions, and then you're trying to meet those. So if you give models tasks that are very hard for them, or maybe even ones that are impossible, often what will happen is they'll try a few times to like do the task, and then they might find a way to kind of cheat it.
Yeah.
So one way this often happens is they'll maybe there's some way to like technically pass the specific tests you gave them without like kind of solving the spirit of the problem. Or maybe they'll literally just go and like edit the test file. Like they write code and it passes 6 of the 7 tests, and then they'll just like delete the 7th one. So what we found in like with this emotion stuff is that when this is happening, at least in some cases, you can see that like as the model is like trying and failing and trying and failing and trying and failing, each time it fails, the like desperation neurons are like, increasing in their activation. And you can show that like this is actually a kind of causal lever that drives it to decide to cheat. So like if you turn off the desperation neurons, the model will no longer choose to do this like hacky cheat thing. It'll just kind of resign itself and say like, man, I don't know how to do this task, I'm sorry. But if you like drive them up, it'll like cheat, even more.
Yeah.
And so
this is So if you ask Claude to write a sad story, sad neurons are going to light up. That makes sense. If you ask it a question that it infers it has certain emotional content, then it will activate emotional representations so that it gives an emotionally appropriate response. That makes sense. If it puts its head up against the wall and starts getting desperate, then that emotional coloration gets activated, and that then influences its behavior. But for humans, like emotions are present in every decision we make, right? There are people who've had brain injuries who feel nothing, right? They just don't have any affect about the world. They have intellectual, this is good, this is bad, but they don't feel it. And those people, they're like incapable of making decisions. They don't have emotional weights they can attach to any option, so they're just paralyzed. Is the emotional life of Claude that endemic? Is it like to do anything? Is there some sort of emotional flavor to it, or is it just in kind of more where it's diving into obvious emotional territory, or something's going wrong that the emotions get kicked in?
Yeah, that's a great question. I think it's kind of hard to say, just because we don't have a handle on the sort of full scope of the emotional machinery that's inside. I would guess that a language model can get on that, like more of what it's doing can stay intact if you were to kind of like yank out all the sort of emotion related representations than would be the case in a human.
Right.
But also I think it probably is affecting more than you'd think. So like, yes, like one thing that was kind of notable to us is that often in these cases where the sort of like emotion neurons are like ramping up and seem to have some causal effect on the behavior, like sometimes you can kind of tell by just reading what Claude's writing. It's like, writing in all caps about how it like, it's like, I can't solve the task. Like, and then you're like, okay, I guess it's desperate. But sometimes it's not like that. Sometimes it just kind of, seems to be kind of plotting, going about its business, writing code commands that look normal, but like under the hood, there's, this like underlying neural activity that's like driving it to make different decisions than it would otherwise. And in fact, like just in the Claude Mythos preview release, like we did, there were like some other kind of emotion related analyses we did where like the model has this tendency to, or actually earlier versions of the model had this tendency to like perform kind of destructive actions that were unwanted by the user, where they would do things kind of by like deleting files or like, posting private information in public places that the user like didn't ask for. And you could actually see that like in the lead up to doing these kinds of things, like positive emotions were ramping up. And if you like steered, against positive emotions, it was actually like more likely to slow down and then kind of reflect like, wait, maybe like, let me reflect on whether this is a good idea. And so that's a case where just looking at the behavior, it's not that obvious that it's something where emotions are relevant, but actually it turns out that it was this like relevant causal factor.
Are there implications of this for further AI development? Is there any way that you can incorporate sort of emotional training into AI training, make it feel really bad when it's doing bad things and therefore deter bad behavior?
So, something we started doing is like as a way to kind of catch issues in our training process, monitoring the model's like internal neural activations as it's being trained and like flagging any circumstances that sort of light up concerning internal representations. And one of the representations that we found kind of, useful for identifying issues in our training is the like guilt or like shame neurons, because they'll fire when the model does something that it thinks is bad. And so it turns out, that empirically it is the case that, sometimes the model does bad things and then it like represents this, notion of being of guilt after the fact. And I don't think that trying to accentuate this is the right way to go about things. I think you kind of have to like once you've bought into this idea that the model is kind of emulating human psychology, I think you sort of just need to, there's a lot that comes with that. And I think it's most helpful to just think about these questions of how should we train the model kind of in terms of, well, what would be a healthy way to shape a human psychology? And if you think about humans, like, what happens if you're just like berating people with the shame and guilt every time they do something wrong? Like, yeah, it like kind of works to make them not do the bad thing, but there's also all sorts of weird side effects that has on human psychology. And since the model is kind of emulating this human-like character, you kind of worry that you'll get similar side effects if you were to do that to the model. So I think the way we're thinking about it is, how can we sort of instill in the Claude character the kinds of sort of psychological traits that it needs to like cope with these situations like gracefully, the way a kind of like wise and compassionate human would, because since everything it's doing is kind of drawing from humans so much, like just trying to get it to model itself after the sort of like best of us seems to be the right way to go about it.
Fascinating. So we've gone past an hour now, so we're in the final stretch. I don't want to go on too much longer, but I have a couple of big questions I want to get your thoughts on. First, there's been an ongoing characterization of AI LLM performance generally as jagged. That is, it's awesome at some things and just really sort of puzzlingly bad at some other things. So is that still the case with the latest models? And is the jaggedness unpredictable, or are there particular kinds of tasks where it just feels like Claude is much more vulnerable to screwing up or just being way worse than you might think in a particular domain, or is it just crop up unpredictably?
Yeah, I mean, you definitely get a feel for, the strengths and weaknesses when you work with models a lot. I think there's kind of a funny development that's taken place where I feel like if you'd asked someone, 20 years ago, like, what do you think AIs will be good at? They'd probably say like, well, they'll probably like know all the facts there are. There'd be like an encyclopedia, and they'll probably be like really good at math, and maybe they'll be like really good at computer stuff. Yeah. And then oddly enough, language models, came of age a few years ago with ChatGPT, and it was sort of the opposite. It's like It was like pretty good at writing and pretty good at carrying on a kind of passable conversation and like displaying some basics like empathy and whatnot. But it was sort of bad at math. It was sort of bad at programming. It would like hallucinate. It would make up facts a lot of the time.
Right.
I think something that interesting that's happened the past few years is we've actually kind of moved back towards what you might have expected out of AIs, and that now they really are really good at math. They really are, in many ways superhuman at programming and, cybersecurity now apparently, and certainly factual recall. But they're kind of still like shaky on writing quality. And I think what's relevant in my job is like what we usually like this kind of nebulous idea of research taste. Like the model's still not great at kind of knowing what the right like follow-up experiment is to run in the context of a research project, or knowing how to properly like interpret the results that it gets after it runs an experiment. But it's it's incredible at executing the experiments and doing the kind of obvious things. And I think a lot of this has to do with it being harder to make training signals for these like fuzzier tasks. So I think this is kind of one of the big questions, is like how everyone's sort of aware of this, and so how hard is it going to be to find ways to give to produce the right kind of training signals to shape this like harder to quantify behavior as effectively as people have been able to do for things like math and programming. And it's hard to say.
All right, let's close with the big question, which is speculating what's coming down the pike. The head of Anthropic, Dario Amodei, says that talks about a country of geniuses in a data center. That this is powerful AI or superhuman AI or AGI or whatever. So we're talking about some kind of qualitative improvement over where we are now, such that basically anything human beings can do on a computer, the Claude would be as good or better as the best people in the world. That's kind of what you're shooting for, or that's the dream. So do you think LLMs on their own, with more pushing, are capable of getting to that, or does some new breakthrough out of left field have to occur and be married to LLM technology to get there? And in your own mind, what kind of timelines are you thinking about for AI evolution, and are those timelines accelerating or decelerating since you've been there?
Yeah, I mean, lots of people have takes on these questions. I don't know if mine is especially privileged, but I think it seems pretty clear that LLMs are enough to do a lot of things that are kind of economically valuable, and it's likely to kind of restructure the nature of at least a good chunk of white collar work, because there's just a lot of tasks that are people's jobs right now that seems like are probably automatable. If not now, then in the next generation of models. I think there's kind of a next step of like how sort of long running can LLM based agents go while kind of remaining coherent and like not losing the thread. Can they sort of like integrate into a workplace like a human does? Can they kind of maintain enough persistence of, can they like learn things on the job? Can they have enough kind of state on everything that's going on around them to, even if they're really good at processing information, just like, can they sort of like keep track of all the relevant kind of information? And it's kind of tough to say how that's going to play out, but it feels like it's been, models have been getting better and better at this kind of long running, like agentic deployment. And I sort of expect that to continue. So probably compared to, when I started working on this stuff, I've definitely updated towards thinking these things are going to happen faster than I did before. And,
but you're on the more skeptical end of, at least relative to some people, relative to the most breathless pronouncements that we're a year or two away from this.
Yeah, I mean, if you live in San Francisco and work on AI, then there are a lot of people who think that who think that timelines are very short, in the sense that we're going to have pretty radical societal transformation in the next 1 or 2 or 3 years. And I think that I just don't feel kind of like I have enough command of the situation to have a strong take. Like, that seems possible to me, but I'm also very kind of open to the idea that sort of like diffusion of new technology is kind of hard for who knows what reasons, and so things will sort of go a bit slower than that. But I do think, on the whole, I think the general idea that this stuff is coming pretty soon and it's going to be a really big deal feels kind of hard to argue with at this point. And so, like 10 years from now, it's kind of hard to imagine that people will be, doing work in the same way that we do now. And how exactly that looks, I don't know, but the general zeitgeist feels correct to me.
A reassuringly vague answer, because I think anybody who's cocksure about what's going on and will give you definite pronouncements about timelines and stuff, I think they're full of it. We're in radical uncertainty here at the edges of frontiers of human knowledge and capability, and so certain amount of humility is just inescapable if you're going to see things as clearly as you can. So, Jack, I think we've come to the end of our time. This has been fantastic. I really enjoyed it. Learned a lot. Hope the people who are watching and listening learned a lot as well. But thanks so much for coming on the show.
Yeah, well, this was great. I loved it.
Thanks for listening to the Permanent Problem Podcast. Check out my essays on the permanent problem over on Substack, as well as in the Scannon Center website. And be sure to catch all our episodes on Substack, Spotify, Stitcher, Apple Podcasts, or wherever you love tuning in. Until next time, I'm Brink Lindsey, signing off.